Greetings. So we'll continue our discussion on fluids, and let's talk about osmolarity, osmolality, and tonicity. Because again, if we don't clear some of this content, it's going to confuse us throughout when we start to expand on this concept and apply this concept. Okay? So again, we go back to our two compartments. One of them has 1 kilogram of salt dissolved in 1 liter of fluid, water, solvent. 4 kilo, and the other compartment has 4 kilograms of salt that is dissolved in 1 liter of solvent, and there's a semi-permeable membrane. So water is going to go from where it's more to where it's less, or from a less concentrated solution to a more concentrated solution. In this case, it's going to go from here to here. Okay. And this continues till the water content in each compartment is equalized. So you see here that water compartment now expands. Why? Because there's more water that goes in from here to here. Okay. And this pressure that moves the water from here to here is pressure of water. Okay. And it's called osmotic pressure, right? Because something is pushing this fluid from this compartment to this compartment. Okay. Now this is very, very important. It depends on the number of particles that are there in each section. So if I have more particles here, less particles here, I'm going to have osmotic pressure that is going to move fluid from here to here because this has more particles and this has less particles. Okay. Now, the key is to know that the osmotic pressure is dependent on the number of particles and not the mass of the salt. So in other words, it doesn't matter if it's 1 kilogram or 4 kilograms. It matters how many particles are there. Well, how does that come to pass? So if I have two solutions, one compartment has glucose, the other one has sodium chloride. So see, I'm now changing what's dissolved or what's a solute in each of these compartments. And then I mix it in water. When I mix sodium chloride in water, how many particles do I get? I get a sodium and I get a chloride. Remember, we talked about that in the last video. How many particles do I get with dissolving glucose? I only get one because it doesn't break down into an anion and a cation, right? Anion, cation, right? So I have one particle I get here and I get two particles here. So if I dissolve one molecule of salt and one molecule of sugar in my compartments, I'm going to have two particles. Even though it's one molecule, I get two particles in the salt compartment and only one particle in the, you got it, glucose compartment. So if I put a semi-permeable membrane, the water is going to go from where the particles are less to where the particles are more. So it doesn't depend on the weight of glucose or the weight of sodium chloride. It depends on the particles that are dissolved in compartments. Okay, it's a very, very important concept. Now, why does all of this matter? Right? Oh man, we've been talking about compartments and all of this stuff, solutes. Well, here's the deal. So I have my intravascular space, I have my cell. So this is intracellular, and this is interstitial, right? Remember, if you're not sure, cover my first video. Okay, so let's say there's a few particles here and then there's lots of particles. So there's a few particles in the intracellular space inside the cell. There's lots of particles in the interstitial space or outside the cell, but not in the blood vessel. What's going to happen? The fluid is going to go from inside the cell to outside the cell to the interstitium or the interstitial space. And the cell is going to become smaller because the fluid's moved out. Vice versa. Let's take a look at another case. Let's say you have less solutes in the interstitial space and lots of solutes in the intracellular space. What's going to happen? The fluid is going to move inside the cell and the cell's going to swell up or get bigger. Cells do not like it when things contract or swell it. So this hydration of the cell is actually dependent on what? Is dependent on interstitial space and how many particles are in there compared to how many particles are inside the cell. Okay? So that's how fluid or water moves through from interstitial space to inside the cell through osmosis. Well, Prashant, how does fluid move from intravascular space to interstitial space? Now that's a great question. Let's just look at it very quickly. The way to remember this is I have an equation. The fluid that moves from intravascular space to interstitial space is based on this formula, K times H minus O, and I want you to remember it. You're going to see this again coming up. K is inflammation, H is hydrostatic pressure, and O is oncotic pressure. Very simply put, hydrostatic pressure is what pushes the fluid out. Oncotic pressure is proteins and other things in the blood that pull the blood, the plasma back in again, or the fluid back in again. So the net total of the fluid that gets pushed out is hydrostatic minus oncotic pressure. What's pushed out and what's pulled in. Now, it is also a function of how leaky the blood vessel is. The more leaky it is, the more fluid is going to go from the blood vessel to the interstitial space. And the leakiness is determined by inflammation. And so inflammation, so that's times H minus O, hydrostatic minus oncotic. This gives you how leaky it is. This pushes it out from intravascular to interstitial. This pulls it in from interstitial to intravascular. And this is the fluid that goes from intravascular to interstitial. Then from interstitial to intracellular, whether it's going out or in actually depends on osmosis through a semi-permeable cell membrane. Okay? So that's how the fluid is moving. We'll explain this equation in detail in just a bit. Okay? So we talked about osmotic pressure. Remember, intracellular and interstitial depending on the number of particles. So next thing you know, hey, if number of particles are important, how do I measure it? And it's got to do with a concept called mole. So 1 mole is 6.023 into 10 to the power 23 particles. That's Avogadro's number. And what's special about it? If I have a molecule that weighs X grams, that molecule's molecular weight is X. X grams of that molecule will have 6.023 into 10 raised to the power 23. So if I have X, right? So let's say if I have a compound Y, okay, and compound Y's molecular weight is MWY, okay? So MWY grams of Y is going to have 6.023 particles in it. If I have Z, molecular weight of Z is MWZ. So MWZ grams of Z is going to have 6.023 into 10 raised to the power 23 particles. So this number turned out to be special. It's called 1 mole. And these are the number of particles that are there. And essentially, from mole comes the word osmol. And that's how we measure how many moles. Okay, so that helps me determine um, how many particles I have. Okay, so 1 mole of glucose gives me 1 osmol of glucose when I dissolve it in water. Remember C6H12O6? Okay, when I dissolve sodium chloride in water, I'm dissolving 1 mole of sodium chloride, but it's actually giving me 2 particles each. So 1 of sodium and 1 of chloride. So it's actually giving me 2 particles. So essentially I have 2 osmoles of sodium chloride when the sodium chloride is dissolved. So when I look at this, 1 mole of glucose in 1 liter gives me 1 osmol, 1 mole of sodium chloride in 1 liter in this compartment gives me 2 osmoles per liter. Okay, guys with me on this? So I have 1 particle, 1 osmoles of particle here and 2 osmoles of particles here. If I put a semi-permeable membrane, because of osmosis, water is going to move from where it's more or the particles are less, which is this compartment, to this compartment here where the particles are more and water is less. Okay. And if you see here, I have 2 osmoles per liter. So remember, concentration was what? Mass over volume. Okay. Now, osmolarity has an L in it. Liters has an L in it. Osmolar. Literity. Osmoliter. So, number of particles divided by volume. That's actually the key. Gives me osmolarity. Osmolality is when I have fluid, when I have, so again, osmolarity is where my bottom denominator is expressed in volume. Osmolality is when I'm talking about number of particles and I want to see how much mass of solute is it dissolved in. So instead of volume, I go into mass. So if I talk about I have 2 osmoles in 1 liter, liter is volume. It's the space that's taken up by the solution or the solvent. If I say I have 2 osmoles in 1 kilogram of water, this 1 kilogram is weight. Okay. Now this is osmolality, lity. Okay, so osmolarity, liter, liter, liter. Okay, liter, osmolarity. Now, again, some people may think, well, it's osmolality. It has an L and liter has an L. No, I want to actually look at larity sounds like liter. Lality doesn't sound like liter. Larity sound like liter. Which one's the one we're going to use? Osmolarity, because it's more practical. That's what we're going to use moving forward. Which one is more accurate? Osmolality is more accurate. Why is that? Because when we change the temperature, the volume changes. So in other words, if you have butter, right? The weight of the butter, let's say, is 1 kilogram. And the volume, so let's say you go to a store and you purchase butter, okay? And it takes some space, right? Um, so let's say it's got a volume X centimeter cube, okay? When I put it on uh, a container and I warm it up, what happens? The butter melts and its volume changes. It's no longer that X cubic meter. However, the weight remains the same. Okay, so I get it. Yes, osmolality, which is mass or weight, is more accurate. But what I use is what's more practical, which is osmolarity, liter. Okay, so now you know this, right? Okay, so let's go ahead and apply this. Okay, but before we do, let's talk about let's revisit how the fluids go from the blood vessel to the interstitial space. So remember we talked about that formula K times H minus O, which is inflammation times hydrostatic pressure minus oncotic pressure. This is how the fluid moves from the blood vessel, intravascular, to interstitial. Okay, so let's go through this together. So let's say you have a blood vessel here. Okay, this is my blood vessel. This is an artery. This is, again, the blood vessel has an arterial side and a venous side. So what's behind the artery? It's the left ventricle of the heart. So the closer you are to the squeezing of the heart, the higher pressure you're going to experience. The further away you are from the pump of the heart, or the left side, left ventricle of the heart, the less pressure you're going to have, right? Right? And that's a very simple concept. So if you're on the arterial side of this blood vessel, which is this side, you're going to have a higher blood pressure, higher pressure of the blood. So let's say that blood pressure, higher pressure is 90. Okay. How did we come up with 90? Again, it's an arbitrary number I'm giving just for an example. Usually blood pressure has a top number and a bottom number. Top number is systolic, bottom number is diastolic. Now, I can use some calculations, which is I'll go something like mean arterial pressure equals systolic plus 2 times diastolic divided by 3, which now gives me one number which is representing my blood pressure and not two numbers. Okay? So when I apply that concept, I get one number which is 90 millimeters of mercury, which is my pressure on this side of the blood vessel. On this side of the blood vessel is a vein. This is the venous side of the blood vessel, and so I'll have a lower pressure, which is, let's say, 50 over 30. So when I apply the same concept, systolic plus 2 times diastolic, okay, divided by 3, I get approximately 40 millimeters of mercury. So here, the blood is being pushed out with hydrostatic pressure of 90 millimeters of mercury, which is my blood pressure. On this side of the blood vessel, I have 40 millimeters of mercury. That's my hydrostatic pressure. Okay, that's what's being pushed out. So that's hydrostatic pressure. Now I have proteins in my blood, and they generate a force called oncotic force. Oncotic force. And they pull fluid inside the blood vessel. Now, because the protein remains the same in a blood vessel, the oncotic force is the same for the most part. So let's say it's 50. So I have here oncotic force of 50 pulling things in, and hydrostatic force of 90 pushing stuff out. So I have 90 pushing it out, 50 pulling it in. So net 40 is going to go from 40 of water is going to go from intravascular space to interstitial space here on the arterial side. Okay, what about the venous side? Well, the fluid that was being pushed out was being pushed out with hydrostatic pressure of 40 and was being pulled in by oncotic pressure of 50. So here on this side, the fluid is being pulled in with 10 millimeters of mercury. That's the water that's going to go inside. So again, now when we extrapolate this, the general trend is, so again, this is the arterial side, this is the venous side. You're going to have fluid that's generally going to tend to go out from intravascular space to interstitial space on the arterial side, and it's going to be pulled back in on the venous side. Now, again, you see it's being pushed out by 40 and pulled in by 10. So there's a difference between how it's pushed out and how it's pulled in, right? So that difference is the fluid that remains in the interstitial space, right? And that goes through what we call lymph channels into lymph nodes, and then it goes back into the circulation. And when we review immunology and we look at lymph nodes and lymph system a little bit, that's where we're going to discuss this. But this is how fluid goes in and out of the interstitial space. It goes into the interstitium, goes out of the intravascular space, and then gets pulled back in on the venous side. Does it make sense? Yes. You want all the good stuff which is being pushed out by the heart to bathe the cells. And for it to bathe the cells, it needs to get out of the blood vessel, go into the interstitium, bathe the cell. However, it's all out. It needs to come back in. So otherwise, you're going to have all this extra fluid in the interstitial space. And it gets pulled in by the oncotic pressure, and whatever remains goes through the lymph channels, which is also perfect because it plays a role in the immunity. Aha. Okay. Now, what does this K stand for? Which is the inflammation. So again, we're going to look at immunology, but this is actually part of the immune response. What if you get a bacteria? What if you get trauma? What if you get stuff that needs to where immune system needs to kick in and mount a response? Well, your blood vessels, part of that immune response is the blood vessels actually get leaky in that area. And when they get leaky, you have more proteins and more plasma that leaks out in that area that causes swelling. And we're going to look more at that when we look at immunology. But again, that increases the fluid going into the interstitial space. Okay? So let's do a quick recap. Well, let's talk about the last part of this before we do a recap of this video or this part. We're going to talk about applying what's going to happen. So we've talked about how things move from intravascular to interstitial space just a second ago, which has got to do with K times H minus O. That's how the fluid moves. Okay, so now I understand that. Okay, so now I have fluid here. Okay, fluid here, and I have fluid here. Okay, now let me give somebody, you know, some fluid, and that fluid, okay, is going to be isoosmolar. Isoosmolar, what does that mean? That means if I have my blood, okay, and it's got a certain concentration of osmoles per liter, my fluid is going to have the same concentration of osmoles per liter. Okay, you guys with me on this? Perfect. Okay, so again, that fluid comes in here. Okay, so with this fluid over here, what happens is the electrolytes. Remember, we talked about when we were measuring blood, some things remain the same between these two compartments. That's the intravascular and the interstitial compartments. Got to do with electrolytes. Very, very important. So the fluid leaks out because of this equation, and the electrolytes move as well. Okay, but essentially the intravascular and interstitial space is going to equalize and get the same concentration. So if I give somebody fluid where the concentration of the fluid is same as that of their blood, okay, essentially I'm not going to change the concentration of this compartment here. And if I don't change the concentration of this compartment, osmolarity of this compartment, these two compartments have already equalized. Why is that? That is because the water keeps moving till the two compartments have the same concentration. Might be of different solutes, but it's the same concentration. So here's the fun concept. The concentration of intravascular is the same as concentration of interstitial, is the same as concentration of intracellular. Because electrolytes move, water move, and then water moves between here and here, and electrolytes move. But electrolytes don't move freely. I'll talk a bit more about that. But water moves, and its movement is governed by osmosis. Here, the water movement is governed by K times H minus O, and the electrolytes, move through based on higher and lower concentration. But all three areas, after a while, the concentration becomes the same, and they're in an equilibrium. So if I give somebody fluid with the same amount of concentration as their blood, it's called isoosmolar, same as body's osmolarity, same number of particles per unit volume as that of blood. It's not going to change the concentration or the osmolarity in this area, which means there's not going to be any fluid shift in this area, right? Now I give somebody hypoosmolar fluid. What's going to happen? Well, again, this becomes, again, I'm giving somebody more fluid and less number of particles. This is going to decrease the osmolarity here, which is then going to further decrease the osmolarity here, which is going to increase the water, decrease osmolarity. What do you think will happen to the cell? That water is going to go from where it's more to where it's less. It's going to go inside the cell. And this cell is going to swell up. Ah, now I give somebody a hyperosmolar solution, which is high number of particles per unit volume compared to what's regularly in the blood. What will that do? It will increase the particles in the interstitium per unit volume, or it's going to increase the osmolarity in the interstitium. Okay, increase number of particles, increase osmolarity. Water is going to move from where it's more, which is inside, to outside to make sure all three compartments have same osmolarity. So when water moves out, the cell is going to shrink. And here the cell is going to expand or swell. Okay? But this is what's really, really important about this concept is that my osmolarity change in the interstitium, which can happen because of my osmolarity changes in the blood vessel, actually directly affects how hydrated or dehydrated my cells get. And it can make a significant difference in whether I live or die, because the cells, if they swell up, will lyse, and if the cells shrink, they're not going to do well either. So just to recap, we talked about what in this video? We talked about osmolarity, liter, which is number of particles per unit volume, which is which helps us understand uh, how much osmotic pressure is between the two compartments. We had osmolality, which is more accurate because it's mass of solvent instead of volume of solvent. Okay, so we talked about that as well. So we're going to use osmolarity, and again, it's the number of particles. We talked about how it causes cells to swell, or how it causes them to dehydrate. We talked about how fluid moves through different compartments, uh, and how fluid osmolarity changes between different compartments expand and shrink the cells. Okay, and then again we talked about how the fluid goes through the from interstitial space to from intravascular space to interstitial space and vice versa. Okay,